Hey guys, Mr. Backerberg here. In this video, we're going to look at cardiac output. So the number of liters of blood that your heart pumps in a fixed interval of time is called your cardiac output. For a person at rest, it might be 5 or 6 liters per minute, but during strenuous exercise, it might be as high as 30 liters per minute. Now, cardiac output can also be altered significantly by some sort of disease. So if you're a physician, how can you measure a patient's cardiac output without interrupting the flow of blood? One technique that doctors use is to inject some sort of dye into a main vein near the heart. So the dye gets drawn into the right side of the heart, it's pumped through the lungs, and then out the left side of the heart into the aorta, where its concentration can be measured every few seconds as the blood flows past. Okay, so here's what we did. We took a healthy resting patient, we injected 5.6 milligrams of dye, and then we took measurements over a period of time, and what we're measuring is the dye concentration over this time frame. And then we took that table of values and we turned it into a graph. So along our horizontal axis, we're measuring the time. Along our vertical axis, that's our dye concentration. And then we've got this function or this graph, which came from that data that we measured earlier on. So what we want to do is figure out how we can use this graph to measure the cardiac output, which is going to be measured in liters of blood per second. Now, in order to calculate our cardiac output, here's the method we're going to run through. We're going to take our milligrams of dye, and we're going to divide that by the units of area underneath our curve. Now, there's a little bit of manipulation that we can do with this fraction. The units of area underneath the curve really come from taking the concentration of the dye and multiplying it by the amount of time. So the top is going to stay the same, but on bottom we're going to change that to say the concentration multiplied by our time. Now, to calculate the concentration of the dye, what we're going to do is take the milligrams of our dye and divide it by the liters of blood. So again, the top of our fraction is staying exactly the same, but we said that concentration is the milligrams of our dye divided by the liters of blood. Now, as far as the time, right now we're measuring in seconds, so we're going to multiply this by the number of seconds that have gone by. Now, we don't typically like to divide by other fractions, so what I'm going to do is take this fraction right here, separate it off of this other fraction, and instead of dividing by a fraction, we're going to multiply by the reciprocal. So I'm going to leave the milligrams of dye on top of this fraction, and I'm going to leave the seconds on the bottom of the fraction, but then I'm going to multiply by the reciprocal of that blue boxed fraction. So then this will be the liters of blood divided by the milligrams of our dye. And then we should notice that we've got the milligrams of dye happening on top and the bottom of these separate fractions, so we can cancel those out. And what that's going to leave us with is a measure of liters of blood per second of time. So now we're ready to start actually doing some computations like a cardiologist. So in this example, what we're going to look at doing is estimating the cardiac output of the patient whose data appeared in the table from a couple slides ago. And we're going to give our estimate in liters per minute. So as we're looking at our graph, the tough part is going to be calculating the area underneath the curve. We don't have any geometry formulas to calculate the area under an irregularly shaped region. And using our RAM program in our calculator is pretty useless unless we have an actual formula or equation for the function. But we can still use some rectangular approximation to help us out. And we're going to use that midpoint rectangular approximation because that's going to give us the best estimate of what our area underneath the curve is going to be. So if we look at our picture with a bunch of rectangles drawn in, now what we've done is every 2 seconds, we've got a rectangle happening in here. So each one of these base values across the bottom of our rectangles, that's going to be a time of 2. What we need to do is we're going to have to estimate the height of our rectangle just from taking a look at our picture. And then what we'll do is find the area of each rectangle and then add all of those areas together. And then we'll have to finish our calculations based on that area that we get. So if we look at this first rectangle, we know the base across the bottom is 2. So we're going to take 2 times whatever we estimate the height of that rectangle to be. Now as we're looking at this vertical axis, it's counting by ones. And what I notice is that it's a little bit less than 1.5. So I'm going to call that 1.4. So that's going to give us the area of our first rectangle. But then we're going to have to add on the area of our next rectangle. So again, we've got a base of 2 for that rectangle, and we're trying to estimate the height of our rectangle in here. Now it's a little bit less than 6.5, and maybe even a little bit less than that 0.4, so I'm going to call that 6.3 for that one. Looking at our next rectangle, again, we've got a base width of 2, and we're trying to estimate that midpoint in there. We are about halfway between 7 and 8, so I'm going to call that a height of 7.5. Looking at our next rectangle over, again, we've got a base length of 2, and we're estimating the height in here. Now, we're between 4 and 5. We're closer to 5 than we are to 4. I'm going to call that 4.8 for my height. Then if we look at our next rectangle, again, we've got a base width of 2. We're trying to approximate this height in here. We're between 2 and 3. It's kind of similar to that last one, so I'm going to call that 2.8 for that height. Our next rectangle over, again, has a base of 2. Looking at calculating the height there, again, we're estimating it's between 1 and 2. It looks pretty close to 2, so I'm going to call that 1.9. Our next rectangle over, again, has a base width of 2. Now this one is just a little bit higher than 1, so I'm going to call that 1.1 for the height. Looking at our next rectangle over, again, we've got a base width of 2. Estimating the height here, we're lower than 1, but a little bit more than halfway. I'm going to call that a height of 0.7. Looking at our next rectangle over, again, we've got a base width of 2. Estimating the height in here, it looks like we're at about the halfway point between 0 and 1, so I'm going to call that 0.5. The next rectangle over, again, has a base width of 2. Estimating the height in here, it's a little bit lower than a half, maybe that's like 0.3. Our next rectangle over, again, has a base width of 2. Estimating the height in here, it's a little bit lower than the last one that we looked at, so maybe that's at 0.2. Our next rectangle over, again, base width of 2. It's even just a little bit lower than that previous one, so that's maybe 0.1. Now, there is technically a rectangle underneath this last piece, but it's not even high enough for us to measure in there. So even if we went with a base width of 2, the height is almost 0, so that's kind of negligible. That's not really going to add anything to our area in there. Now, if we were to go through and calculate all of these different areas and add all them together, what we're going to end up with is 55.2. Now, we're measuring this in milligrams per liter, and what we're going to have to do is multiply that by our seconds. So now I'm going to jump back to our previous slide real quick. We said to actually calculate the cardiac output, we're going to take the milligrams of dye that we started with divided by the units of area underneath the curve. So we just calculated the area, that was that 55.2. We need to take our 5.6 milligrams that we started with, and we're going to divide that by our 55.2 milligrams per liter, and we're multiplying that by our seconds. But if we remember from the very beginning, we didn't want to give our estimate in seconds. We wanted to give our estimate in minutes. So we're going to have to convert these seconds over into minutes. So we know that there's 60 seconds in 1 minute. So this is going to allow me to cancel out those seconds in there. Now, if I do the multiplying on top, 5.6 times 60 is going to give me 336, but then I still have to divide by the 55.2 on bottom. Now, if we look at the top, this is being measured in milligrams. On bottom, we have this milligrams per liter, but then we also have minutes in here. Now I notice that with these labels, we've got this fraction in here. And again, we don't typically like to divide by fractions. So what I'm going to do with this label in here, this milligrams per liter, I'm going to multiply by the reciprocal, so the liters per milligram. So this is no longer in here. What that's going to allow me to do is cancel this milligram label with this milligram label. So now what we've got is liters on top and minutes on bottom, which is what we wanted, liters per minute. Now, if we actually do this dividing in here, 336 divided by 55.2 is going to give us about 6.09 if we round that off to 2 decimals. So this represents a cardiac output of just a little bit more than 6 liters per minute for this patient. That's going to be it for this video. Thanks for watching.